Hello and welcome to lecture 6 of the course Reasoning LLMs from Scratch. Since the past two lectures, we have been focusing on the topic of reinforcement learning. In the first lecture of reinforcement learning, we looked at what is the meaning of reinforcement learning, how are RL problems different from supervised learning and unsupervised learning problems. And then we looked at a category of RL problems which are called as multi-arm bandits. In today's lecture, we will start to discuss the core of reinforcement learning, which is finite Markov decision processes. This problem defines the field of reinforcement learning, and we are going to understand this problem completely from the scratch. Uh, to understand this problem, we'll first start by defining a structure which is called as the agent environment interface. Remember in the first lecture about reinforcement learning, we said that there is an agent which interacts with the environment around it, and then it gets more and more experiences from the environment and learns and becomes better and better to achieve a reward or a goal. Now we are going to formalize this intuition in the form of this agent environment interface. What this interface says is that there is an agent at the center of the reinforcement learning problem. Now, this agent is receiving information from the environment about the state of the environment, and the state is denoted by S of t. So, at every time step, the agent is receiving some sort of an information from the environment, which is denoted by S of t. And then, based on the information or the signal the agent receives from the environment, it is going to take a certain action. And this action is denoted by A of t. And then, after the agent performs this action, one time step later, the agent is going to receive a reward from the environment after this action is performed, and then it is going to go into a new state. Now we are going to follow certain certain nomenclature when we define the state, the reward, and the actions. The states are always represented as capital S of t. Capital denotes the set, and small s, for example S1, S2, etc., these denote the actual value of the states within this set. Similarly, actions are denoted by A of t. The action set is denoted by A of t, and individual actions within this action set are denoted by A1, A2, A3, etc. And then, in a similar fashion, the reward set is denoted by R of t, and then individual rewards are denoted by R1, R2, R3, small letters, etc. So the agent receives a state, which is a signal from the environment S of t, and then it takes an action based on that signal. And then after it takes an action, the agent or the state is going to change. The agent is now going to receive a new state from the environment, which is denoted by S of t plus 1. And then, along with this state, the agent also receives a reward. So the state and the new reward go hand in hand. The new reward is denoted by R of t plus 1. This is the structure under which we are going to work in the remainder of this lecture. So let us go ahead. Now, what happens is that you might be thinking about, okay, after it receives this state, how does the agent perform this action? Is there some kind of a mapping which tells the agent what action to take? So the answer is yes, there exists a mapping from every state to the probability of selecting each possible action in that state. And this mapping is called as the agent's policy. So the policy is the mapping from every state of the agent to the probability of selecting each possible action from that state. So this mapping is called as the agent's policy. In a way, the policy is what dictates what actions the agent is going to take whenever the agent receives a specific signal from the environment. And we denote this policy as pi of t. And this notation also you will see often, pi t a given s, which means that given the state s, the probability that action A is chosen is given by this policy. So A given S, action given the state S. That is how we have to read this symbol. Now let's try to understand some examples of states. Examples of states are, let's say, sensor reading, then an intermediate position while playing a chess game or playing a Go game. There are some abstract notions of states as well, which are, let's say, I'm going to office, but I'm not sure where my car keys are. So uh, that governs the state of my mind. So state is also an abstract notion where if I'm interacting with a person, then before I have any conversation with a person, uh, whatever memory I have in my mind about my relation with that person can also be thought of as a state. A state is whatever information you can give to the agent to enable it to perform an action within an environment. That is the meaning of a state. Now, examples of actions can be, let's say, voltages applied to motors of a robotic arm, whether or not to have lunch, or pedaling wheels of a bicycle when a small child learns to ride the bicycle for the first time. So there is a difference, right, between states and the environment. States is like the information that you have, and then uh, actions are the sort of decisions that you take once you get the information from the environment. That is the difference between states and actions. Now we'll start to understand the agent environment interface with some practical examples, which will concretize your understanding about this interface and how to formulate problems in terms of the agent environment interface. So the first example that we will take is that of a bioreactor. Don't worry about what a bioreactor does. Even I'm not exactly sure about the workings of a bioreactor, but we don't need to know that. All we need to know is the bioreactor is a machine which is used to produce useful chemicals, and the way it does that is by having some sensors which takes readings, and then based on the readings, uh, it tries to achieve a certain temperature and a certain stirring rate within the bioreactor. Now, given this much information, let's try to think what are the states, actions, and rewards in the agent environment interface. So, what are the states? The states are the information we receive from the environment. So, these are the readings of the sensors and the readings of the thermocouple. What are the actions? The actions are the target temperature and the target stirring rate which I am reaching within the bioreactor. So, to achieve the target temperature, I will turn on my heating element and activate my heating element. To achieve a target stirring rate, I will activate the motors within the bioreactor. So, these are the type of actions that I will take based on the information that I get from the environment. And what are the rewards? The rewards are the moment to moment measures of the rate at which useful chemical is produced in the bioreactor. So you can see that states are vectors, but the reward is a single scalar. For example, the states can be written as this vector, where the first element of the vector is the sensor reading, and the second element of the vector is the thermocouple reading. And actions can be written as this vector, where the first element of the actions is the target temperature and the second element is the target stirring rate. And then the reward is just one scalar which says that, okay, based on the states and actions, my reward is going to be the rate at which useful chemical is produced. So once you define this agent environment interface, the agent is going to optimize the policy in such a way that the reward is maximized, which means that it's going to maximize the rate at which useful chemical is produced within the bioreactor. Let's take another example so that you understand how to formulate problems in terms of agent environment interface much better. Let's take an example of a pick and place robot. These are common robots which you see in warehouses of industries where you have to pick objects and place them on a conveyor belt. So, here my reward is pretty clear. My reward is going to be uh, +1 for all the objects that I have picked up and placed. And I'm going to assign a small negative reward for a jerky motion, which means that I'm going to penalize my robot if it does some weird actions and manages to pick up objects. I want it to pick up objects, but in a smooth and steady motion. Now, what are the states and actions in this case? The the states are the readings of the joint angles and the joint velocities, which means that what is this angle, what is this angle, and how fast are both these angles moving. Once I have this information, I'm saying that that is all I need in order to predict the dynamics of the pick and place robot. So these are the information I'm getting from the environment, which is the angle of these joints and the rate at which these angles are changing. And then actions are the voltages which I apply to the motor at each joint. There is one angular motor which is present at this joint, and there is a motor present at this joint. And because of these motors, these arms are moving, and the robot has a degree of freedom which allows it to pick the objects and place it in a position. So the states are the readings of the joint angle and velocities, and the actions are the voltages which are applied to every motor at each joint. And the reward is +1 for all the objects taken, picked up, and placed, and a very small negative reward to avoid jerky motion. And again, this can be summarized in terms of these vectors. The states are theta 1, omega 1, theta 2, omega 2, etc. The actions, which are the voltages, are V1, V2, V3, etc. And the reward are +1 for success and -0.02 for jerky motion. So, this is the first section of today's lecture where you should be clear about what is an agent environment interface. Uh, and how to formulate problems in terms of the agent environment interface. We are going to stay restricted to this interface for quite a long time as these lectures on reinforcement learning proceed. So it will help you much better if you understand this interface nicely. Okay, so now let us move to the next section, which is the section on goals and rewards. So far, we have been talking about rewards, right? But we haven't really uh, looked at rewards more closely. All we have seen is that the agent is given a reward to maximize. That's it. And then it learns a policy so that it achieves this reward or maximizes the reward in the long run. And the use of a reward signal to actually formalize the idea of a goal is one of the most distinctive features of reinforcement learning. And the reason we say that is because if you look at all other AI categories of problems, which include supervised learning as well as unsupervised learning type of problems, there is no goal or a reward which the agents are trying to achieve or the model is trying to achieve. Either the model is trying to classify between different objects, or the model is trying to find a hidden pattern in the data which it is shown. But reinforcement learning are the only classes of problems in which the agent is trying to maximize the reward in the long run. But now we'll try to understand this much more closely. So, how do we define the rewards for different problems? Let's say we are playing a game of chess. In this case, the rewards are pretty straightforward. The reward is plus one if I win the game of chess. The reward is minus one if I lose the game of chess. And if I draw the game, I'll not get any reward and the reward is zero. If a robot is, if I want to make a robot to escape a maze as fast as possible, then the reward is going to be minus one for every time step that passes before the robot escapes the maze. Why is the reward minus one for every time step? Because as the time step increase, your reward is going to be more and more negative. So the agent will try to escape the maze very fast so as to get the maximum reward in the long run. For example, if the agent takes 10 time steps to escape, then the reward is minus 10. Whereas if the agent takes 2 time step to escape, then the reward is minus 2. This means that the agent is going to reduce the number of time steps it takes to escape so that the reward increases in the magnitude. Then, if we are making a robot collect empty soda cans, then the reward is plus one for each can collected, otherwise, the reward is zero. This is kind of similar to the pick and place example where we had a reward of plus one for every object successfully picked. Now, we'll try to look at one one subtlety while formulating the rewards. You might be tempted sometimes to give a reward for sub goals. For example, in the game of chess, if we give a reward of plus one for taking the opponent's queen, what this will do is that it will confuse our agent. The agent will not know whether it's supposed to win the game or it's supposed to strategize the move such that the queen of the opponent is taken. So, reward should not be given for achieving sub goals, but for actually attaining the final goal. This is very important. And many times while formulating problems, I've seen that we tend to get stuck in these sub goals because we think that maybe this is easy for the agent. But unless we give the final reward or the final goal that we want to achieve, our agent will get stuck in achieving these sub goals and it will not achieve the final goal that we want it to achieve. Okay, so now comes a very crucial distinction. We are going to distinguish between individual rewards collected at each time step and the total return or the expected return at each time step. So, the agent's goal is to maximize the addition of all the cumulative rewards it receives in the long run. And this means that we want to maximize the expected return. So the expected return at time t is denoted as capital G of t, and we express it as follows. Capital G of t is equal to the reward collected in this time step uh, and the addition of all the subsequent rewards which the agent collects in the future. Okay, so let's look at our diagram which we had drawn over here. You see here, the question that you ask is that, okay, what is the reward which your agent is collecting? So the reward is RT plus 1. Now, if you ask me the question, what is the expected return? Then the answer is not RT plus 1, but the answer is addition of all the rewards collected from this time to the time the episode ends or the task ends, which means that RT plus 1 is just going to be the beginning of the addition of the rewards. After that, we have other terms which are RT plus 2, RT plus 3, RT plus 4, etc. Basically, we want to add all the rewards after the time step t, and this is what is called as expected return. So there is a crucial difference between individual rewards and expected return. And in reinforcement learning problem, the agent's goal is to maximize the g of t, which is to maximize the expected reward it collects in the long run. So, okay, now this is the formulation for expected return. Remember, I said in my last sentence that we have to add all the time steps till the time the episode ends or the task ends. That's why this formulation is suited for applications in which there is a final step. For example, game of chess. Once a person wins a game of chess, the episode is over. We move on to the next episode. If we are playing a robot escaping a maze, once the robot escapes the maze, the episode is over. We restart the episode. So, in all these applications, there is a final time step for which this formulation of the expected return makes sense. But now consider cases which are so these are called as episodic tasks. Uh, Now there are also cases where the agent and environment interaction it goes on continuously. There is no stop. For example, let's say we have the Chandrayaan mission. So there is a rover being sent to the moon, and this rover is going to continue its expedition for a very long time. So there is no limit to the time in which the robot is going to continue to move and continue to analyze rocks, water, etc. This is an example of a case where the agent continues to interact with the environment continuously. There is no stop to that interaction. And these type of tasks are called as continuing tasks. So for these tasks, we cannot use the above formulation because if you if you are at a particular time step, let's say I start when Chandrayaan is sent to the moon and I add all the rewards. So the rewards will just keep on adding, 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 and it might reach close to infinity. That is why we have to give certain priority to certain rewards. For example, what we say now is that whenever we have these continuing tasks, whatever rewards are received immediately are much more valuable than the rewards which are received way into the future. And this is called as the concept of discounting. We'll try to understand this with a simple analogy. Let's say if I have a 100 rupee note in my hand right now, and I ask you the question, the 100 rupee note is valuable right now, will the value of this note be same 5 years later? And the answer to this question is no, because of inflation with the same 100 rupee you are able to get less items as compared to the number of items you might get right now. So the value of this note keeps on decreasing as time passes on. Similarly, if the rover goes to the moon, then whatever rewards it collects immediately or uh, in the near future are much more valuable compared to the rewards it collects much later in time. And this is called as the concept of discounting. So we say that immediate rewards are much more valuable compared to the rewards which are received later. And we take this into account by saying that every reward is gamma times less valuable than the reward received one time step before. And here gamma is the discount rate which is less than 1. So we change the formulation of expected return like this. We say that g of t is equal to r of t plus 1 plus gamma times r of t plus 2 plus gamma square times r of t plus 3, etc. So what we are doing with this is that let's say gamma is zero point 0.5. So the second reward is multiplied by zero point 0.5. The third reward is multiplied by zero point 0.5 square, which is even less than zero point 0.5. The fourth reward is multiplied by 0.25 into zero point 0.5, which is equal to 0.125 RT plus 4. So the importance of each reward goes on reducing as you move farther and farther away from the current time step. So this reward is gamma times less valuable than this reward. This reward is gamma times less valuable than this reward. And then finally we add all these rewards up. So for tasks which are not episodic, for tasks which are continuous, this is how the expected reward is formulated. Now, if gamma equal to 0, the agent is only concerned about immediate rewards, because g of t is equal to rt plus 1. And as gamma approaches 1, the agent considers future rewards more strongly. So we can control this importance given to the immediate rewards and the future rewards by controlling the value of gamma. This is the main concept which I want all of you to understand in this section, where we discuss about the difference between individual rewards and expected return. And the formulation of expected return is very different for episodic tasks and for continuous tasks as well. We will try to understand this with a very nice example, and the example is that of uh, a pole and a cart system. So what happens here is that, let's say, whatever I have drawn in black is the pole and this is the cart. Now, if the cart is stationary, because of gravity, the pole is going to come down. So the objective here is that I want to apply forces to the cart in such a way that the pole does not fall over. So if I move it a bit front, then the pole will go back like this. So again, I have to push it in the backward direction. Then again, I have to push it in the forward direction. So intuitively, I can see that there is some kind of oscillatory motion which I need to move the cart in so as to keep the pole stable in the upright position. But the question which I want to ask all of you is that, given this problem statement, how would you write the rewards and returns for this problem? Now, I want all of you to pause here and think about this, because we want to consider two different formulations, one for episodic tasks and one for continuous tasks. Okay, let's see and go ahead. So, first is to treat the problem as an episodic task, which means that when the card falls over, the episode is over and we restart the project. So here we say that the reward is plus 1 for all the time steps when the pole does not fall over, and the reward is 0 for all the time steps when the pole falls over. Now, when we write our expected return like this, what it means is that if, let's say, the pole falls over after two time steps, my reward is going to be 1 plus 1, that is 2. If my pole falls over after five time steps, my reward is going to be 1 plus 1 plus 1 plus 1 plus 1, that is plus 5. So, to maximize my reward, my agent will try to maximize the time step until which the pole falls over, which is exactly what we want. This means that our reward formulation is correct, because if the reward formulation is like this, my agent will try to keep the pole upright for the maximum amount of time. Now, the second case is where we treat this problem as a continuous task. So, let's try to understand this now. When we are treating this problem as a continuous task, the reward given is minus 1 for failure, and otherwise the reward given is plus 0. So you see, it is slightly different than the way we write rewards for an episodic task. And now you will understand why this is the case. Let's say the agent falls after two time steps. Okay, so what is the expected return in this case? So for the first time step, the robot is or the pole is upright, so the reward is 0. And for the second time step, also the pole is upright, so the reward is 0. But for the third time step, what we have is, we have gamma to the power 2, and here we have minus 1, which is equal to minus gamma square. Now, if gamma is equal to zero point 0.5, this is going to be minus zero point 0.5 square, which is equal to minus 0.025. Uh, this is going to be 0.25. Okay, so this is going to be negative of this. Now let's say the pole falls over after three time steps. So it's going to be 0 plus 0 plus 0 plus gamma to the power 3 minus 1, which is equal to minus zero point 0.5 cube. It is equal to minus 0.0125. Now, which expected return is greater? Is it this or this? It is this, because even though the magnitude is smaller here, there is a negative sign, so this is greater than this. So to maximize the expected return, what our agent will try to do is that it will maximize the amount of time steps till the time the pole falls over, which is exactly what we want. So this formulation also works perfectly for us because it says that if with this reward formulation my expected return can be maximum only if the pole stays upright for the longest amount of time. So this is where we come to the difference between episodic tasks and continuous tasks and how to formulate the rewards and expected returns for both these classification of problems. Once we have understood this, we now move to the next section, which is the main section which we want to cover today. After defining the returns, the agent environment interface, we come to the Markov property. And I want all of us to build a very nice and strong intuition about this property so that even if we forget all the formulas later, we still remember this property because our intuition is strong. Okay, so firstly, a state signal is the signal which the agent receives from the environment before it takes any action. So it's synonymous to the state of the environment, but here we are calling it as a state signal because it is a information which the agent is receiving from the environment. Now let us look at some examples where the state signals have a very specific property. Whenever we are speaking with someone, whenever we are having conversation with someone, the entire history of our past conversation with this person is known to us, and this entire information is stored in our mind, and we are speaking by accessing this information which is already stored in our mind. In the game of chess, the current configuration of chess pieces contains the entire history of the past configurations. In other words, if I am making a move as a chess player, I need to know only the current configuration of the chess pieces of my board. I do not need to know the configurations that have happened in the past at all. So, in a way, the current state or the current configuration of the chess pieces is holding all the relevant information I need to take my next action. Now, let's say that there is a cannonball and it's firing cannons, and let's say the cannons are going like this. Now, if you ask me what is the next position of this cannonball, I do not need to know these at all. All I need to know is what is the position and velocity of this, and I can predict the next position of the cannonball. So, again, it's like all the relevant information it is stored in this state. I do not need the values of positions and velocities of all the previous states. So, the past history does not matter. What is common in all the above examples? In all of these examples, the state signal, which is the knowledge of people you are talking with, the current configuration of the chess pieces, the current position and velocity of the cannonball, these the state signal retains all the relevant information from the past. You do not need to go back in the past and access all the data from the past. The current information is stored entirely in the state signal. And a state signal that succeeds in maintaining all the relevant information is said to be Markov, or said to have the Markov property. So we can of course define it formally as well, but I want all of you to make this intuition strong. Whenever we have a state signal which has all the property, let's say a cannonball or the current chess configuration or speaking with someone, then all the relevant information is contained in that state. So the state is said to be Markov or have the Markov property. Now let's define this property formally. For most general cases, the dynamics not only depend on the current state but also depend on everything that has happened earlier. So this is called as, or this is the most general case which is non-Markov, and it can be expressed like this. This is, I'm going into a bit of mathematics, but it's really not very complicated. So just follow me along. So this is the probability that the reward received from the environment is R, and the next state which the environment goes into is S dash. Now what we are saying is that the reward and the state are not only dependent on the current state and the current actions, but it is dependent on all these past events, which is S0, A0, R1, S1, A1, R2, S2, A2, R3, etc. But if the state signal has the Markov property, then all we need is we need ST and AT. We do not need the information that is stored in all the past events. In other words, the probability that RT plus 1, which is the next reward, is small r and the next state is S dash, only depends on the current event, which is the current state and the current action which is taken by our agent. It does not depend on all the events which have happened in the past. So, if a state signal has a Markov property, it allows us to predict the next state and the expected next reward given the current state and the current action. So now we'll look at some practical examples to demonstrate the Markov property. And if you have understood the property that we have discussed via intuition and also via the mathematical formulation before, you will be able to follow these examples very nicely. So let's say we again look at the pole card system, and we say that the state signal, which includes the position of this card and the velocity of this cart, the angle between the pole and the cart, and the angle at which this, or the rate at which this angle is changing. If I have all this information with me, that is all I need to predict the dynamics of the pole cart system. I do not need to know what happened in the past. I only need to know the current position and velocity of the car, the current angle and angular velocity of the pole with respect to the car. That's it. Then I say that the state signal has a Markov property because it allows me to predict the motion of the pole card system in the future. I do not need to know what happened in the past. So the state signal is retaining all the relevant information of the past within the state signal. But you would ask the question, is this true in reality? The answer is no, because in the real pole card system, there are some other parameters which are going to influence these dynamics, which is the bending of the pole, the temperature of the pole and the wheel bearings. So the bearings over here, the bearings over here. So there are some other parameters like the pole bending, the temperature of the bearings, which are going to affect the dynamics of the system. So just by knowing the position and the velocity of the cart and the pole is not going to help me predict the future dynamics. So in the real setting, it's going to be, this state signal is going to be non-Markov. But in this setting, in an idealized setting, this state signal, which is given by p dot theta and theta dot, is going to satisfy the Markov property in an idealized setting. We will take another example, which is the game of draw poker, you don't need to know the specifics of this game to understand our discussion, but all you need to know is that for for a person to play a perfect game, and for the state to satisfy the Markov property, the player should know or have the knowledge of one's own cards. For example, if I am playing this game, I need to have the knowledge of my cards. I need to see what are all the bets which are made by all players in the past. What are the number of cards which are drawn by these players in the past? Then my past history with all these players. For example, does Raj like to bluff? Does his expressions reveal something when he is bluffing? Uh, does Sridhar bluff a lot or he does not like to bluff? Now, if I have all this information, then this is the relevant information that I need to play my next move. But in a game of poker, no one remembers this much information unless you are James Bond in a Casino Royale movie. So, in a real setting, no one knows this much information, and maybe we remember 10% of this total information before we play our next move. So the state representations which people use to make poker decisions are non-Markov because the state does not retain all the relevant information that is needed to play the next move. These are some of the examples in which you can apply the definition of Markov property that we discussed in practice. And now we move to the next section, which is Markov decision processes. Once we have understood the meaning of Markov property and the intuition of Markov property is clear, we can begin to understand Markov decision processes. Uh, a reinforcement learning task which satisfies the Markov property is called as a Markov decision process or an MDP. You might read some papers in the future or even right now where reinforcement learning is applied in large language models. And you will see this terminology MDPs used quite frequently. So now that you have understood the meaning of Markov property, you are in a very good position to understand the meaning of MDP whenever you come across this phrase while reading research papers. We will look at some notations now. Again, we are in this same system, which is the agent environment interface. And the first definition that we are going to look at is called as a state transition probability, which means that the agent is starting from one state, taking an action, and then moving into a next state. And the state transition probability is what is the probability that the agent moves into the state S dash given the current state is S and the action taken by the agent is A. So this is also represented by this notation where we say that we are choosing the value S dash from this set S of t plus 1, we are choosing the value S from this set S of t, and we are choosing the value A from this set A of t. Then R of S comma A is the expected reward for this state action pair. So this is the pair when the agent is receiving state S from the environment and taking an action A, then what is the expected reward from the environment for this state action pair? And then R of S comma A comma S dash is if I started in S and I took action A and I landed in S dash, then what is my expected reward? So this is really a special case of this where uh, you say that okay, I'm in state S and taking action A, but I also land in the state S dash. So what is my expected reward in that case? These terminologies are simple. Don't get bothered by the notation too much. But you might hear me saying transition probability multiple times throughout this course. And whenever I'm saying that, I want you to refer back to this definition where we are saying that it's the probability that the agent transitions from one state to the next state. Now, as the last part of this lecture, we are going to understand a very practical example about to illustrate Markov decision process in detail. Similar to the Roomba robot, which people use in their homes these days to clean the dust, this is an example of a recycling robot where at every time step the robot has to make a decision whether to actively go and search for a can, whether to stay stationary and wait for someone to bring the can, whether to go back to the home base and recharge the battery of the robot. So imagine that a robot is moving and the battery is high. So of course the robot will keep on moving. But if the battery is low, then either the robot can simply wait to conserve the battery, or the robot can go back to the home base to recharge the battery. So there are multiple actions which the robot needs to take depending on the state of the robot. Now, what is the state set here? The state set has two possible states, which is high and low. And the action that I take are three. Either I can wait, either I can actively search and pick up cans, and either I can go back and recharge myself and increase my battery level. So these are the states and these are the actions. And then, how do we formulate the rewards in this case? Let's try to think about that. So, obviously, we want to give the highest reward when the robot is searching and collecting the cans. So, let our search denote the expected number of cans which the robot collects while searching. So, let's say if our search is 3. So, I say that whenever my Roomba robot is moving in a room, it's going to collect 3 cans. But if the robot is waiting, then my reward is not going to be very high because I don't know how many people will go and put the can inside this robot. So the reward for that is our wait, but our search is going to be greater than our wait because I want the robot to actively search and collect robots actively. And then let's say while moving, suddenly the robot's battery dies, which means that your robot has not planned the battery conservation properly, and the reward is going to be negative for this. In this case, the reward is going to be -3 because the battery is discharged and it has to be rescued. Now, what we'll do is, okay, one last definition. After that, we'll move ahead to the exciting part. A period of searching which starts with a high energy level leaves the robot high with a probability alpha and reduces to low with a probability 1 minus alpha, which means that if I am a robot and I have a very high battery level, then it will remain high with a probability alpha, but eventually the battery is going to reduce and it's going to reduce it to low with a probability of 1 minus alpha. And if my battery is low, then my battery can remain low with a probability beta, but there is also a chance that the battery will get depleted, and the probability for that is 1 minus beta. Now, what we'll do is we will try to write the transition probabilities and the rewards for this example. So, let me just delete this first. Okay, so here we have 5 different columns. The first column is the state, the current state of the robot. The second column is the action which the robot is taking. The third column is the new state in which the robot is moving into after it takes an action. The fourth column is the probability that the robot goes into this state after being in this state and taking this action. And the fifth column is the reward that the robot gets after being in this state, taking this action, and going to the new state. So let's now try to understand this by taking a lot of examples, right? Okay, so first, let's say the robot is in the high state, which are the first two cases which I have outlined over here. So we'll try to first understand this. Don't look at other rows at all. If my robot is has a battery high, then and my robot is searching. So if S is high and A is search, then there are two possible options. Either my battery will stay high or my battery will become low. In both of these cases, the probability is going to be R search because my robot is still searching. Now we'll consider the second two cases where my initial state is low. If my robot state is low and I am searching, there are two possibilities. either the next state will remain low, which means I still have my battery, or my battery is completely over and I have to be rescued, in which case the next state will become high. So now, in the first case, the reward is still R search because my robot is still searching. But in the second case, my reward is negative because I have to rescue my robot, which is not ideal at all. And the next case is if my state is high, my robot is waiting, then obviously S dash will also be high over here because if my battery is charged and I'm not doing anything, my battery will stay high. But the reward I will get here is R wait, which is less than R search because I'm waiting for someone to come and place the cans in my bucket. And the last two are if I am low and I'm waiting, my state will stay low and I get a reward of R wait. And the final state is if my state is low and I go back to the charging station, I recharge, my state will become high. But the reward here is zero because I'm not collecting any cans. So at this point, pause in the video, make a table and write down the states, actions, next state, state transition probabilities, and the rewards. Once you have written this, you will get a lot of confidence. For me also, it took some time to reach to a stage where I have understood this table properly. But once I did, it gave me a lot of satisfaction that okay, I am able to write down the state transition probabilities easily. Now, uh, because the state signal has a Markov property, probability of S dash only depends on S and A. It does not depend on what your Roma robot did in the last 2 years or in the last 2 months. It only depends on the current state and action. That's the power of expressing reinforcement learning problems as Markov decision processes. Now, this entire explanation can be summarized with a very nice transition graph, and the transition graph looks like this. So at first glance it looks a bit complicated, but it's actually very interesting. So let's say my robot battery state is high. If my battery is high, I have two options: either I go and actively search or I wait. If I am actively searching, then either my battery will stay high or my battery will become low. In both these cases, my rewards are R search because I am still searching. Now, the second option when my level is high is to wait. If I wait, my state will still remain high, but the reward I get will be R wait in this case. Now, if my battery level is low, I do not have two options, but I have three options now. Either I can search, I can wait, or I can recharge. If I go and search, there is a possibility that my battery will stay low, which is good. Then I get a good reward. But if my battery dies down, which is quite possible because my charge is low, then I get a very bad reward because the robot has to be rescued in this path. Or either I can search, or if I wait, then my battery will stay low, in which I will get a slightly low reward of R wait. And the third option is go back to the charging station and recharge. So I'll go from low to high and I'll get a reward of zero because I'm not collecting any cans in this process. So this is how the transition graph can be drawn. After you have written this table, you can actually spend some time drawing this graph. It's a good experience to get confidence in this subject. So to summarize, we finally wanted to reach towards Markov decision processes, but then before that we had to do a big build up. We started with explaining about agent environment interface, how to construct problems in terms of an agent which is receiving states from the environment, taking actions based on that states, and then achieving the maximum reward with the reward goal. And we saw two examples here. The first example was of that of a bioreactor, and the second example was that of a pick and place robot. In both these examples, we looked at how to define these problems in terms of an agent environment interface. What are the states? what are the actions and what are the rewards. Then we looked at what is the difference between individual rewards and expected returns. Expected returns is the cumulative sum of all the rewards the agent is going to get starting from that time step and going into the future. And then expected return is what the agent tries to maximize in the reinforcement learning problems. The formulation for expected return is different for episodic and continuous tasks, as we saw in the pole balancing problem, where we looked at how the discount rate gamma was used in the formulation, and how it says that rewards in the immediate future are valued more compared to the rewards later, and the value of gamma actually controls the importance that we are giving to the immediate rewards and the future rewards. Later, we looked at what is the Markov decision property, or the Markov property, which states that a state signal has the Markov property if it retains all the relevant information from the past. We looked at an example of a projectile. We looked at an example of conversations with the person, or playing a chess move where only the current configuration of the chess pieces matters before you play the next move. And then finally, we looked at Markov decision processes, where we said that state signals having Markov property and reinforcement learning problems constructed from these state signals are said to be Markov decision processes. We looked at an example of a recycling robot where we actually wrote down the transition probabilities and the rewards that we are collecting. And finally, we looked at a transition graph. So we are going to look at this example two more times in the next few lectures. After this, this example will be concretized in your mind. Thank you very much, everyone. And I know I got into some mathematics in this session, and we'll keep on going into some mathematics in the subsequent lectures also. So what I'll do from next lectures is that wherever there are derivations or proofs, I'll do that in the appendix after the lecture is over. So whichever students want to skip that part, they can skip it and they can still follow the remaining lecture. Having said that, the mathematics in RL is not very complicated, and I'll try to make it understandable for all of you. Thank you very much.